I am your organizer, Michelle Beacom, Managing Editor of CIM Magazine. Just a little housekeeping before we get started. To ensure you have optimal audio, if you joined by computer, make sure you've selected the computer audio button. If you're using phone for your audio, please make sure you've selected the phone button. If you have any questions during the presentation, please select the question mark and type them into your question box in the GoToWebinar control panel. They're underneath the question mark here, and the questions will be held until the Q&A period after the presentation. And now I will introduce today's presenter. Brady Hostetler is Senior Technical Sales Consultant at Honeywell Technologies. Brady is a process and industrial technology professional with experience in advanced automation, process solutions, and engineered combustion systems, helping organizations leverage Honeywell technology to improve operational performance and efficiency. Now, without further ado, I'm going to turn it over to Brady.
All righty, thank you. Let's get this loaded. Are we live?
Perfect. Thank you.
Perfect. All right. Thank you. Yeah, thanks for the introduction. So yeah, I'm Brady Hostetler. I work for Honeywell Technologies. I'm a technical sales consultant. The consulting has obviously taken years off my hairline, so sorry for the old photo there. But we'll jump right into it. So good morning, everyone. This is a quick introduction on improving recovery and throughput in mineral processing with computer vision. We're all aware a vast majority of concentrator plants already run on a control system that measures flows and everything. This is a focus on computer vision. All right, so here's where we're going today. First, why computer vision? Then I'll cover 2 machine vision solutions that we've installed across the world, C+ froth and C+ rock. Then the part that actually matters, which is what you do with the signals once you have them. I'll briefly show some process examples, taking the vision measurements to control. And I'll finish with like what a deployment would look like if you want to try this at your facility. All right, so why computer vision? Here's our problem, you guys. Advanced process control is only as good as the signals feeding it. So your typical controller, like I said, you can see flows, levels, pressures, densities, tonnages. You can see them continuously, and you can usually see them reliably. And then you can also see mineral samples and sizing from your lab. But this is, typically every 20 to 60 minutes or however often that you run lab results. And now what we know actually drives recovery, for example, in these magical flotation cells, is froth formation, bubble structure, and stability at every cell, and also particle size distribution entering the cell. All these direct characteristics lead to better recovery and flotation, but none of it is available with standard instrumentation. So the problem is you're not maximizing your recovery because you're not maximizing your measurement capabilities. Controllers reject the disturbances they can measure, okay? The ones they can't measure, they just absorb. And then your operators usually fill that control gap with their own little twist, which means the plant inherits that operator's variability shift to shift. So these characteristics I mentioned that drive further recovery are hard to get with conventional instrumentation, but they're all sitting there in an image, right? Computer vision. So if we attach a camera, here's some things we can get. The outputs such as velocity, bubble size, granulometry, anomaly flags, they all land on an OPC server as tags, okay? Your APC reads them as controlled or disturbance variables, even manipulated variables, the same way it would read a flow transmitter. From the controller side, there's nothing unusual about these tags from our computer vision solution. And multivariable control is sensitive to what you feed it. So those grinding and mixing targets in your plant depend heavily on aggregate particle sizing. Most controllers today they're inferring that from mill power and bearing pressure and maybe some other variables. So it's an inference rather than a direct feed of particle sizing. So among these signals that we can extract for that, they can also work as inputs to digital twins and machine learning models. So they sit alongside whatever you've already built rather than competing with it. And lastly, you get continuous measurement instead of a sample every 40 or so minutes from a lab, or you don't have to infer off an operator's read of what the froth or aggregate looks like in that moment when they were walking down the line. Okay. But we've got two products I've kind of hinted at, and both of them run as a plugin to our Honeywell APC platform, or they can even integrate with third-party APCs. That's not a huge issue. We have more than 700 instances of our C+ froth solution running on flotation cells today, and we've just started rolling our C+ rock solution out. We've got over 16 conveyor belts utilizing our hardware and software package for both of these solutions. So we'll first talk about C+ froth here. This is pretty much the whole solution, almost the whole solution in one picture. You have a camera above a flotation cell looking down at the froth surface. Those images from the camera are sent to a local server. The C+ running on the server is doing some calculations in the backend, and they're used as a feed for typically an advanced process controller. So a lot of us know maximizing treatment in a concentrator depends strongly on flotation performance, and your operator already judges each cell by looking at it. Okay, these images are basically the operator looking at it. All we're doing is making that judgment quantitative, continuous, and available to the controller with timestamps too, right? So you know exactly when these images are taken and what's happening at those points in your process. So for a typical installation, we'll see about 20 to 25 cameras per server. These measurements are transmitted again to the APC server via OPC, and also even a web-based interface is created for operations to view. So it's not hidden behind a black box. You can also see these images and calculations on a web-based interface, not just a backend to APC calculations. You'll look in the bottom left here, you see the low camera specification, the low resolution. It may seem out of place for machine vision, but it's more than enough, you guys. It keeps the hardware cost and the network load down, so we don't have to use as many servers. And it's definitely sufficient to interpret your process through machine vision, through our software and our algorithms determining that. And the camera, by the way, you see on the slide is generic too. So this can be swapped out for self-cleaning lens designs. You can add lights if you have a certain type of process where you need them. And even enclosures for corrosive applications are made to surround the camera on this. So I just want to enforce your process being dirty, corrosive, dusty. It's not a full stop for a camera solution. There are definitely ways around it that we've done in the back end with our software. All right, so let's dive into what our software then is doing with these images. On the far left is the raw frame. Many of you have probably seen a flotation cell before. This is obviously what the camera sees, but it's a constantly changing surface, right? And it's on its own. It's obviously telling the controller nothing. It's like a kid going, look, there's bubbles. There's not much you can do with that. Okay, so everything to the right is what the model pulls out of those frames. So a couple examples: velocity zones. They're tracked independently. You can see the squares across the cell. They give you exit speed of the froth layer. So you don't want to go too fast on the velocity because the bubbles won't have time to catch those valuable minerals. And then you don't want to go too slow, or those minerals will drop out of the froth layer and sink back down. So it's a very delicate balance, sometimes what we call flotation magic. And now we're turning that magic into reality by viewing these zones. Second, bubble segmentation, where every bubble boundary, you can see the red outlines a little bit there. It's extracted and sized to develop a distribution. So the idea is to maximize your surface area of the bubble to get the best extraction. And that's our point of segmenting these bubbles. On the far right, maybe you guys have seen this before. It's a breakage event inside the measurement zone of a froth cell. So this can be classified and flagged as an event for your operator. And I mentioned the operator walking up and down the line to check the cells and how they're looking. In this case, with these breakage events detections, the operator isn't staring at the video 24/7. Okay, they got a bunch of other things to look at on their screens. And instead of trying to monitor this continuously for sunken cells or breakage events, you'll get an alert of a process error if something were to occur in your cell. So a couple examples of what this machine vision can do for froth flotation. How exactly do we extract these variables from a camera? I can't give away too much. This is already a lot, but I'll try and walk through it. Just don't ask me too many questions on this, because what I'm about to say is the bulk of my knowledge of how these neural networks work. Okay, so essentially what we do is we take that camera stream, do some pre-processing, attach a froth classifier, install a buffer, and then develop an aggregated output. So the classifier in the middle there, it's a neural network operating over texture features from what they call a gray level co-occurrence matrix. And it classifies each frame independently to determine, for example, if it's stable froth, unstable froth, or if there is a breakage event occurring. So this could be very server intensive. Remember, we want to keep our hardware costs down, but we do some pre-processing to smooth things out. And remember, we have that pretty low resolution camera for video feed. So we're trying to lower our hardware limits, and we do that through the camera and through the pre-processing module. Anyway, those predictions from the froth classifier accumulate in a buffer, an inference buffer, and then the final classification output is issued periodically from that buffer rather than going each individual frame. Okay, that's what makes the signal stable in terms of our breakage event detection enough to alarm on. So we're not getting noise by a single frame. You don't get nuisance alerts or alarms. We definitely know operators do not want nuisance alarms. And that's why we hide the classification behind a buffer, so we can build operator and let's call it even controller, advanced process controller trust as well. All right, so let's look at let me start this video. Let's look at the breakage model. Make sure it's muted. Look at the breakage model in action. Take a time to take a sip here. You can see, so you can see the bubble surface being segmented in real time in that square. Almost real time, right? We have that buffer to remove noise from the machine vision algorithm. After that classifier and buffer work in the back end, the aggregated output you can see on the right gives a reading from the froth layer. So stable, unstable, breakage. You see the stable in those green dots, you see breakage in yellow, and just maybe take a look at the bottom as well. So that's the aggregated output over several frames of the video feed. So if you're seeing at the bottom, there's some instances where there's one breakage detection, that yellow square. The model is removing that noise because the other frames are stable. So we're trying to remove those nuisance alarms by taking that aggregated output with a buffer. That's where we're getting more reliable differences between a stable froth and breakage events. All right, now onto the other machine vision application. This is C+ rock. So same idea here, guys, just a different part of the process camera over the belt, and again, running as a plugin to Honeywell APC or integrated with a third-party APC. And in this case, a lot of us know maximizing treatment depends on how well you characterize the mineral on the belt. And knowing your feed lets you optimize ahead of a disturbance instead of reacting to it once the mill tells you about it, once your grinding process tells you about it. And on top of that, knowing when conditions are unsafe protects your belt and the grinder, preventing full stoppages. Definitely something that we do not want is full stoppages of your grinding process, especially if you don't have a stockpile to continue your flow downstream. This could cost millions of dollars in the long run, right? Even over hours. So installation, very similar to the froth application, same camera spec, but in this case, just 2 to 3 cameras per server with results again over OPC. So here we're outputting granulometry every 10 seconds and oversized alarms every second. So a much larger data set, much quicker, 2 different calculations going on as well, and that's what's adding to the server load here. So you can see the 20 to 25 cameras for froth. In this case, we've got 2 to 3 cameras per server for the C+ rock solution. Again, we're taking raw images from the camera, but no size information is available from that alone. We have to turn that into signals for the operator, for alarms, and for advanced process control. So with our C+ software, a few things can come out of a single camera. And you can kind of see that here, rock segmentation across the full belt, which can give total granulometry aggregated from particle measurement. You have empty belt or abnormal object signal detection. That goes straight to the operator. Again, we're removing noise for that as well. And we're also working on a depth map, okay, which gives total volume and volume by region on your belt. And in all these cases, we work with multiple measurement zones with what we call it our intelligent zone selection. So that's what keeps the numbers on this stable. So when things like lighting or belt loading change through a shift, if you have an outside belt and the sun's setting across it, those corrections get made with intelligent zone selection, and it definitely helps with dusty environments. When you have the conveyor rock coming down, it's going to be dusty, you guys. So we have to look for ways around that, and we've done it with light balancing and intelligent zone software. So just to cover it a bit further, we have 3 very established measurement capabilities. So that includes particle size distribution, which is a 10-point distribution every 10 seconds, including coarse, intermediate, and fine percentages. And importantly, this is calibrated against laboratory sampling during commissioning. So it's not just a guess from pixels with no inference to the real world. We're comparing lab data with our simulated results. So kind of like a gray box model for simulation. We're inferring from real world data and analytical data of our algorithms. We also have oversize detection. This is evaluated every second. You can set a configurable size threshold, and separately you can have an accumulated volume alarm. Okay, so you have maybe a stream of medium rocks, a large stream of medium rocks, that's an accumulated volume, or you have a problem which is just one massive boulder on there. Okay, 2 different things to look at. So they run on 2 different alarms and processes. Additionally, we have the anomaly detection. So it's trained on objects that you actually want on your belt, and it can track anomalies like unwanted metal, liners, tooling, and it can even look at empty belt signaling. So is there nothing on the belt coming to your process? Just an example for our C+ rock. This is looking at the granulometry and oversized rock detection. We're running 2 different software models because they have different challenges that require different latency. Okay. So granulometry can afford 10 seconds. So it uses a heavier approach of processing. It's called a dense extreme inception network for edge detection. So it's looking at the edges of the rock and classifying that on a fine-tuned data set to determine coarse, fine, intermediate, and then confirming what's dust or what's rock, and then it gives an estimate of those percentages. On the right is oversize detection. You can't have 10 seconds. So that path uses a YOLO object detector. You only look once object detector. So it fine tunes and goes detect, refine, alarm, accumulate. The belt, you guys have seen these belts, they're moving fast. A missed detection on an anomaly or an oversized rock leads to grinder damage, okay, or a down belt. So the machine vision processing model on oversized rock needs to be quick. So that's why we run these on 2 different models. All right, another quick video looking at the oversized detection. So from the camera to the feeder, I showed on the right, it's about 20 seconds. That's the entire time that the model has to react before bad things happen. Okay, and in the 2 cases on the right need different responses. So one boulder arriving versus accumulated oversized alarm volume building up. It's that same 20-second window. It's why those 2 alarms, volume and oversize, are separate signals. But we need to solve this in 20 seconds so we can give advanced warning to the operator or to the controller. So yeah, just outlining, this is outlining the rocks here. Copal just means big rock, okay? So if you ask my wife about her engagement ring, she'll say it's a copal. I balled out for that. So if you see the numbers, if you see a 1.0 copal, that's a big rock, okay? I forgot to translate that. All right, so now how do we take these outputs and use them for control? Very quickly, just another review on some measurement features. I've got a few more videos to show you just so it's not slides with photos. I don't think I showed this. We've got froth velocity. Maybe I'll get my laser pointer out. You got froth velocity being measured from the camera. You can see the measurement zones. You've got the arrows with the velocity vector and the speed, right? So you can see how big the arrows are and in what direction they're pointing to get a sense of how your froth layer is interacting. Let me get off this so I can go to the next video. Empty cell detection is kind of small, guys, but this is the same as the sunken cell. So you're looking at a measurement zone, looking for sunken or empty parts of the cell where there's no bubbles or froth layer that's producing good recovery yield. I showed you a little bit of the anomaly detection. Here it is again. Oh, this is translated. So you can see in red, it's highlighted. It says big for big rocks here, and it's determining that through edge detection. And then another thing I don't think I brought up, belt misalignment. So you can see, I'll grab my laser pointer again. You can see these red lines looking at the belt alignment across the full width of the belt. It's making sure it's not stacked to one side. Okay, I'm sure you guys have seen where if you stack, there's a lot of rocks stacked to one side, all that weight's on that pulley, and then your belt snaps. Okay, so this is just looking on top of all the variables it can pull and the anomalies it's detecting. We can also look at the alignment of the belt to make sure you have a solid weight distribution across the belt. So good for preventing big mistakes. Again, you don't want a stoppage. This is all helping with the stoppage. I would consider C+ rock. Your benefit is enhanced alarms without an operator needing to look at it 24/7. And then it comes with characteristics and variables for your advanced process controller. 2 very great improvements to your process with just a camera and a server, right? All right, moving on. A signal only pays for itself when something acts on it, okay? So here, it's just a quick example. I just want to show briefly a layered control strategy we use for flotation that utilizes the C++ froth solution. So this is enabled by our computer vision software using froth velocity from those cameras, from that software. That's the variable that links two layers that we're seeing on screen, okay? Mass pull control and grade or recovery control. So for mass pull control, the objective is to keep cells overflowing and reject disturbances arriving from the grinding circuit. So the controlled variable is overflow velocity measured with computer vision. And here manipulated variables have, they include like cell level, air injection, maybe reagents as well. And the disturbance is ore mass flow from grinding. And if you just think about that ore mass flow from grinding, could we use something for tracking the ore mass flow disturbance for this process as well, I wonder. So just maybe hold that thought a little bit. Think about how could we track the input even to flotation. Anyway, the other layer is grade control. The objective is maintaining recovery and hitting target concentrate grades. So controlled variables are recovery and grades. Manipulated variables are the overflow velocity profiles down your bank of flotation cells. So you're gonna have a bank of flotation cells. You have different velocity profiles in each cell. This is being controlled for adjusting grade control. And remember, without vision, without computer vision, these controllers have no controlled variable. And this is just an input to your APC that you might already have existing on site. So in this layered strategy, the grade controller manages grades and recoveries. And the way it does that is by manipulating that froth velocity profile of each line. So an interface block, it's behind the scenes in this case. I could show it to you if you're interested, but it's an interface block that defines the profile and passes it down to the controller as the set point for the mass pull controller. So you can see in each cell, these are different rows of flotation cells, these lines. You can see the velocity declines down the bank. So you pull hard early, then you pull progressively less, your velocity slows as the cells deplete in recoverable material. And then this grade controller decides what that curve should look like. And the mass pull control on the other side delivers it. Okay, and that's all done through the overflow velocity. So pretty neat stuff with just one set point, one control variable from the camera and software solution. Here's an example HMI containing those velocity profiles from the froth layers. Might be somewhat hard to see. I'll use my laser pointer here just so you can see. I just wanted to show you, even this is not our HMI for Honeywell Experion. It's a customer HMI, and it's not even our web interface. So we can develop any sort of visual for the froth velocity. So you see these orange boxes, maybe like a light yellow tinge as well. These are your velocity profiles across your bank. You can see that same like cascading effect of velocity across your rows of banks. Just a good visual for the operators to see what's going on in their process, okay? Again, we don't want it to be a black box. We don't want it to be hidden. There are some calculations in the back end for determining where to set these velocities, but at least the operator can see, okay, these are how my cells are reacting right now. And then maybe if they see it running for a few months, they say this is how it should operate. And if they see some shifting, they can look in their mind and say, okay, something's wrong with my process. Usually this is what I see visually. And now my grade's dropping and my process isn't running properly. So it's good to have that visual there. On the C+ rock end, this is just examples of a belt feeder result. Here we're comparing fines percentage from C+ rock against a laboratory reference. So behind each sample in the graphic here, you can see the actual belt image, and then it's outputting a fine percentage. And these two tables below, they're just laboratory, we'll call them campaigns, that were taken 6 months apart. So when we first got there, we had an average error against the lab. This is just fines percentage, right? The smallest particles we're estimating the smallest particles on a low resolution camera. We had an error of about 3.7% compared to lab. Okay, and then 6 months later, with no calibration, no recalibration between those 6 months, it drifted about 1.5%. Okay, not that bad, especially looking at fines percentage. That's very good deviation, and it's definitely enough to properly control and stabilize your process. So that variability still gets reduced for the average, but we still recommend maybe every 6 months to do a recalibration, just so you're not drifting too far away from a set point. Otherwise, your advanced process controller gets out of whack and everything needs to get redone. But compared to lab, very, very good. And live, right? Continuous. All right, so just one example of a control strategy built on that measurement. This is a real example. This plant feeds a rod mill from 3 conveyors, A, B, and C. The controlled variables you see are tonnage, feed, and coarse tonnage. So the manipulated variables are the conveyor speeds, A, B, and C. They have different, percentage of particle distribution on each conveyor that we're measuring with the camera. And they all contain the C+ rock solution. So we're looking at each conveyor, what's on it, and adjusting that speed. And the control objective is to hold the
Brady, we can't hear you anymore. I can't hear you. For this, there's still people here. So
I'm very sorry. Okay, I'll continue it. I think I heard it cut out even. Like I heard my mic stop making a buzzing noise. Oh, okay. Let me put this on here just in
people are
case.
clapping now. So okay, I'm
Oh,
gonna
thank God.
leave now.
All right, enjoy the silence, you guys. I hope that was good. Just see the slides, and now I'll talk over it. I'll start. Well, here. Are people saying where I ended up at or no? I'll start here, and I can share more slides, or I can share this deck after if we miss something. I want to leave some time from Q&A. So let's start here.
Great. I think that's perfect. And
I'll be quicker.
everybody gets, well, they don't get the slide deck, they get the video, so they will get
Oh, great. So they get me
the
talking to
silent
myself.
part too.
Okay.
Okay.
All right, I'll continue.
Okay, well, thanks.
Sorry about that, guys. So let me run through these quicker than I was. But here, what I'm showing is the rock measurements. You guys already saw this slide, and we're comparing the error average to laboratory test results. So the initial calibration, it was about 3.7% off, and 6 months later, it drifted maybe a point. And the importance of this slide is that we need to recalibrate. Our C+ software maintains its accuracy. And the other point is 3.7% is a pretty good error, okay? And this is comparing the laboratory data of fine particles. So superfine particles, and we're still within 3.7% error. Plenty enough to improve your process and your stability. And plenty enough to, let me go to the next slide, plenty enough to control it. And I'll be quick with this again. Essentially what it's doing is reading coarse percentages on 3 different conveyor belts and adjusting the speed of each conveyor belt to maintain a coarse percentage. But we're trying to maintain tonnage. So we're maintaining the tonnage feed and we're maintaining the coarse percentage using 3 different conveyors to control the speed. And this is just the look at it. I'll show my laser pointer again. I was just showing it to you guys with no. So these are 3 events I want to show, A, B, and C. These are where the coarse tonnage feed increases. Our conveyor speeds are interacting with that. So they're adjusting their fine. The conveyor A had more fines, okay? So you'll see it bump up a little bit to keep the fine speed based on tonnage feed. And then you'll see in C that the conveyor ran out of feed. So this is our tonnage feed. You see this huge disturbance. We ran out of feed. So the other two conveyors had to counteract that within the advanced process control, still trying to maintain that course percentage. And this is with no operator involvement. So even this little blip, no operators looking at that. They just see it get corrected by the cameras and the advanced process control. And it is kind of boring, but what you want is a flat line. I kind of showed this with flat line. You want a flat line, you want stability. I hope I didn't miss much. So this might not be bad. So from assessment to production, I went into this very deep earlier, but I think you guys probably saw it on the screen long enough to get the idea. What I want to drive home here is that before you install the camera, the server, the APC application, the software, we're doing an offline proof of concept with like an iPhone camera. Okay. So we can do this all before commissioning, agree on KPIs before installation, if that's what you're looking for from going from an assessment to production. Right. And then the conclusion, yeah, I just wanted to mention that it's not a replacement to APC, it's a complement. These signals are all something that you can't do with conventional instrumentation. You could look at abnormal conditions earlier, which is very good from a safety standpoint. And really what it's doing is extending capabilities you already have. So a lot of you probably already have advanced process control on your site. This is just an augment to that to get to the next step of optimization in your process. And I hope, I'll go to the end here. I hope I was still on.
Yes.
Good? Okay.
Yeah, it's all good. Sorry, I was talking. I forgot to turn my microphone on. I was a bit frazzled by all
I've
that.
been there. I've been
Anyway,
there.
thank you for the interesting presentation. I just want to remind all the attendees, which many of you state, I'm so thankful for your patience. Just if you have questions, to go ahead and type them into the question box in your control panel. And I'll kick it off with the first question. Can C+ rock be applied to aerial images from ROM or stockpiles?
Oh, we haven't used our exact C+ software for ROM stockpiles, but we have used, our team, our Center of Excellence team has done stockpile calculation. That's a great question. We have done stockpile calculations with cameras and analyzers to determine composition of a stockpile feed. And even further, that we take that information and feed it into a advanced process control and an asset management software that we own that's doing, it gets even more complex. We're taking that information, putting it into a simulation of a process, and in this case it was a roaster, and we're giving the roaster information on the stockpile. So when the stockpile goes through your entire process, the roaster knows how to change and fine tune its variables from our simulated roaster simulation with stockpile information. So that's a very great question. It's a separate installation from C++, but we have done stockpile ROM calculations.
Okay, I have a couple of questions that are along the same lines. How do you keep the camera clean and clear from dust, moisture, etc., in very dusty area?
Oh yeah, big issue. There's great camera solutions out there that have self-cleaning lenses. Okay.
Okay.
I don't want to give away the certain vendor. We like to keep them secret for us because we like to use. But it's a very unique self-cleaning lens to get the dust away. It happens very quickly, and yeah, I think I mentioned it before. Dusty environments are not an issue. We can go about it by lens cleaning, different types of illumination, and the software calculations. And maybe you've seen, like, the lighting matters a lot, because if you're driving in the snow, you can kind of tell if you've got your high beams on, you're like, this is actually worse. I don't want to illuminate the snow because it's reflecting back on me. So it depends on the type of dust. That's why we do that proof of concept to determine
Okay. What is the cell area typically covered by the field of vision from a froth camera?
Oh, that's a good question. Yeah, it depends on the size of the cell. I think it's maybe a meter by a meter, but it could be smaller.
Okay, can C+ integrate with reagent dosing controllers?
Yes. So and that's part of the initial assessment. So we look when we're determining KPIs with you and the return on your investment of this solution. It's an augment. Remember, it's not an entire advanced process controller. So we're augmenting with computer vision. If you already have a way to control reagent dosing, that's amazing, because then we can use computer vision to control reagent dosing. If you don't have it, we're looking at a different ROI, and we've done it before where we say, okay, for you to be able to utilize C+ software, you need already this instrumentation, and regulatory control for these things. So yes, absolutely, we can do it off of.
Okay. iPhone cameras are becoming pretty good. How do the proof of concept results with the iPhone cameras usually line up with the final installation?
If you're really good at taking videos, it's really good. Well, I mean, we give you instructions of how to do it, right? So, I mean, you saw the cameras pointing straight down. That's probably what we want is you looking down with the iPhone camera. Don't drop it in. That's bad news. Look down at the cell and take a video. Maybe one with the flashlight on, one with it off, maybe one with like outside illumination and one with any light whatsoever, because illumination matters. But the resolution on an iPhone camera is way better than what we are using as a camera for the actual solution. So it's going to be good, but minus the illumination piece.
Okay, interesting. Um, okay, here's one. Can proof of concepts be completed without cost?
That's classified. Send me an email.
Okay, okay, that's good. Okay, is the computer vision system fast enough for complete control of the process?
No, it's an augment to advanced process control. So you talked about reagent control, air dispersion, all this stuff. You're already controlling the flotation in some way. This is not taking over. You're not using computer vision as the single source for control. It's an augment to advanced process control.
Okay. Do the cameras capture and report color?
Now, we we are looking into it for in a way color spectrometry to look at mineral not capturing color. I mean, the camera feed can capture color. Yeah, I should walk back on that. It's capturing color in the camera feed. So if you wanted to just look at color over time, we can give a web visual of that. But when we're doing all that pre-processing and the gray occurrence matrix, we're changing that to minimal levels of gray hues, and that would be to reduce server load. Yeah, if you
Okay.
want color as a visual, you can, but you're just adding to your server load.
Okay. How would you integrate these signals into a digital twin or simulation environment for APC tuning and operator training?
Ooh, yeah. So I mentioned that roaster application, which was a simulation where you're taking stockpile information and feeding it into your own fancy little algorithms that I can't. Because I'm not the engineer for one, and I'm going on, but I also can't share it. but yes, that's a good idea. You can definitely create operational training scenarios with these feeds. So the example with those conveyor speeds changing, we can change that into a digital twin simulation, and we can even improve upon the results by testing the theory of those speeds. And then we can also train operators by saying, okay, you're looking at your computer vision solution. This is what's happening here. And you're looking at how your conveyor speeds are changing. What if one conveyor speed drops out? And that's what happens in a real scenario. And you can have them create a scenario that tests the operator on, okay, if a conveyor drops out, what's happening?
Okay. This is the last question I have, unless somebody wants to type in a new question. Here it is. It's how would tighter control of ore size distribution upstream change your downstream recovery or energy consumption?
Yeah, I mentioned the flat line. Stability is important. So getting a stable coarse feed or a certain percentage of coarse is super important for your downstream processing, especially in flotation, right? If you have a very consistent flotation, like nice fine particles, your extraction is going to be so much better. And you're also preventing regrind scenarios or different types of errors in a cyclone. Say you're sending too much into the overflow or underflow of a cyclone for regrinding. Those are all corrections that can be made with computer vision by knowing the feed percentages.
Great. Okay, I don't have any more questions, so it looks like we're going to wrap it up. I'd like to thank Brady for joining us today and coming back and redoing part of it. Thank you so much. And I'd like to thank all of our attendees, as I always do, but especially today for your patience. That was really incredible to see that most of you stayed on the line. Uh, I'd like to ask you that you please fill out the short survey that pops up on your screen at the close of the webinar. A link to the video recording of this webinar will be emailed to you tomorrow. For more online presentations like this one, visit the CIM calendar of events at cim.org. We look forward to seeing you at our next Solutions Exchange webinar. Thank you and have a great day.